Bicimals, binary rational numbers. Concept and operations, Base 2. Revision notes by Decroly Education Centre. Definition of Bicimals. The Bicimals can be referred to as the rational binary numbers. A bicimal is the base 2 analog of a decimal. It has a bicimal point and bicimal places, and can be terminating or repeating. Like decimals, Bicimals are created from fractions through long division. Also like decimals, Bicimals can be converted back to fractions. You convert a bicimal to a fraction the same way you convert a decimal to a fraction, you just work in binary instead of decimal, and use powers of 2 instead of powers of 10. Converting a bicimal fraction into a decimal fraction. The process of converting a binary fraction into its decimal equivalent is done in 2 steps with the numbers the left-hand and right-hand sides of the radix point separately. When looking at converting the binary on the left-hand side of the radix point, we convert it just as we would when converting any binary integer number into its decimal equivalent. Example: 101 in base 2 equals 1 times 2 squared, plus 0 times 2 power 1, plus 1 times 2 power 0, equals 1 times 4, plus 0 times 2, plus 1 times 1, equals 5. Next, we work out the chunk at the right-hand side of the radix point. We do exactly the same thing here as we did on the left, just with the fractional columns. 0.101 in base 2 equals 1 times 2 power minus 1 plus 0 times 2 power minus 2 plus 1 times 2 power minus 3 equals 1 times 1 half plus 0 times 1 quarter plus 1 times 1 over 8 equals 1 times 0.5 plus 0 times 0.25 plus 1 times 0.125 equals 0.625 in base 10. 0.101 in base 2 equals 0.625 in BASE10. So we have a fractional part that represents 0.625 in base 10. So we now combine the integer part, 5, and fractional parts, 0.625, together on either side of the radix point. This gives us the number 5.625 base 10. A terminating bicimal is always easy to convert to a fraction. The numerator of the resulting fraction is the bicimal itself, treated as an integer. The denominator is 2n, where n is the number of bicimal places. Example 1. Convert 0.1101 to a fraction and then to base 10. Solution: 0.1101 equals 1101 over 2 power 4 equals 1101 over 10,000. This is in decimal equal to 13 over 16 equals 0.8125. Example 2. Convert the number 1011.0011 base 2 to base 10. Solution: 1011.0011, base 2 equals 1 times 2 power 3 plus 0 times 2 power 2 plus 1 times 2 power 1 plus 1 times 2 power 0, plus 0 times 2 power, minus 1, plus 0 times 2 power, minus 2, plus 1 times 2 power, minus 3, plus 1 times 2 power, minus 4, base 10 equals 11.1875. Converting from a decimal fraction to a binary fraction, bicimal. This is also done in 2 steps with the 2 sides of the decimal number separately. Example 2. Convert 9.125 in base 10 to bicimal. Solution: we shall have to deal with the left-hand side of the radix point first. 9 will be converted as seen above. 9 in base 10 equals 1 times 2 3, plus 0 times 2 2, plus 1 times 2 1, plus 1 times 2 0, equals 1001 in BASE2. Next we need to deal with the fractional part of our decimal number, which as a reminder is 0.125. Again, there is a simple step-by-step method for performing the conversion. To begin with, we take the decimal fraction and multiply it by 2, IDEST. 2 in base 10 times 0.125, in base 10 equals 0.250, in base 10. We then take the whole number part of the result as the first binary digit after the radix point. In this case it is 0, so we have got as far as 0.125 in base 10 equals 0.0 what? In base 2. Next we disregard the whole number part of the previous result, i.e. ignore the 0 before the radix point, and multiply the result by 2 again. The whole number part of this new result is the second digit after the radix point, that is, 2 base 10 times 0.250, base 10 equals 0.50, base 10. In this case, the whole number part is again a 0, so we have now got as far as 0.125 base 10 equals 0.00 what? In base 2. Again, disregarding the whole number part of the result and again multiply by 2, that is, 2 base 10 times 0.50, base 10 equals 1.0, base 10. Once more, we take the whole number part, this time as the value of the third digit after the radix point. In this case the whole number part is a 1, so we have now got to 0.125 base 10 equals 0.001 what? In base 2. Again we drop the whole number part, but as the fractional part we have left is 0. As we have nothing left we are done. This leaves us with our final representation. 0.125 base 10 is exactly equivalent to 0.001 base 2. Now that we have extracted both the integer part of our original number and the fractional part, we can finally combine them on either side of the radix point. 9.125, base 10 equals 1001.001, base 2. Example, convert the decimal number 11.1875 base 10 to base 2. Solution. First, look at the integer part, 11. Table 2.1. Quotient. Remainder. 11 divided by 2 equals 5 and the remainder is 1, which is A0. 5 divided by 2 equals 2 and the remainder is 1, which is A1. 2 divided by 2 equals 1 and the remainder is 0, which is taken as A2. 1. 1 divided by 2 equals 0 and the remainder is 1, which is recorded as A3. Hence, equals, 10, underscore 0 equals, a 3 a 2 a 1 a 0, base 2 equals, 10 11, base 2. Now let us look at the decimal part, that is, 0.1875. Table 2.2, converting a base 10 fraction to binary representation. 0.1875 times 2 equals 0.375. Here the number after decimal is 0.375, since there is 0 before decimal point, the number before decimal point is 0, which will be recorded as A_1. 0.375 times 2 equals 0.75. Here the number after decimal is 0.75, the number before decimal point is 0, which will be recorded as A_2. 0.75 times 2 equals 1.5. Here the number after decimal is 0.5, the number before decimal point is 1, which will be recorded as A_3. 0.5 times 2 equals 1.0. Here the number after decimal is 0.0, the number before decimal point is 1, which in this case will be recorded as A_4. Hence, equals, 0.1875, base 10 equals, A_, minus 1, A_, minus 2, A_, minus 3, A_, minus 4, _2 equals, 0.0011, base 2. Having calculated 11 base 10 equals 10 11 base 2. And, 0.1875, base 10 equals, 0.0011, base 2. We have, 11.1875, base 10 equals, 1011.1011, base 2. Infinite fractions. Whilst binary and decimal fractions both work on the same principles, each has their own problems when it comes to representing numbers accurately with a given number of digits. In both cases there are certain numbers that will always result in something called a rounding error, where the number cannot be represented exactly and the nearest number has to be used instead. Example, find the binary equivalent of 0.3 is summarized in Table 3. Table 3. Converting a base 10 fraction to approximate binary representation. 0.3 times 2 equals 0.6. Here the number after decimal is 0.6, the number before decimal point is 0, which will be recorded as A_1. 0.6 times 2 equals 1.2. Here the number after decimal is 0.20, the number before decimal point is 1, which will be recorded as A_2. 0.20 times 2 equals 0.4. Here the number after decimal is 0.4, the number before decimal point is 0, which will be recorded as A_3. 0.4 times 2 equals 0.8. Here the number after decimal is 0.8, the number before decimal point is 0, which in this case will be recorded as A_4. 0.8 times 2 equals 1.6. Here the number after decimal is 0.6, the number before decimal point is 1, which in this case will be recorded as A_5. As you can see, the process will never end. In this case, the number can only be approximated in binary format, that is 0.3, base 10 is approximately equal to A_-1, A_-2, A_-3, A_-4, A_-5, base 2 equals 0.01001, base 2. Question, but what is the mathematics behind this process of converting a decimal number to binary format? Answer, let z be the decimal number written as z equals x times y, where x is the integer part and y is the fractional part. We want to find the binary equivalent of x. So we can write, x equals A_n2 power n plus A_n1, 2 power, n1, plus A_0 2 power 0. If we can now find A_0, times A_n in the above equation, then, x, base 10 equals, A_n n1, till A_0, base 2. We now want to find the binary equivalent of y. So we can write, y equals B_, minus 1, 2 power, minus 1, plus B_, minus 2, 2 power, minus 2, plus B_, m, 2 power, m. If we can now find B_, minus 1, times B_, m, in the above equation, then, y, base 10 equals, B_, minus 1, B_, minus 2. B_, m, base 2. Thanks for your attention. Kindly like and share our videos. Please don't forget to subscribe and press the notification bell to be the first to receive the next learning video. You may also give us a comment to suggest what topic you would like us to cover. See you later.